What is a black hole made of?
The term black hole is of very recent origin. It was coined in 1969 by the American scientist John Wheeler as a graphic description of an idea that goes back at least 200 years to a time when there was two theories about light. One, which Newton favored, was that it was composed of particles. The other was that it was made of waves. We now know that really both theories are correct. By the wave particle dualities of quantum mechanics, light can be regarded as both a wave and a particle.
Under the theory that light is made up of waves, it was not clear how it would respond to gravity. But if light is composed of particles, one might expect them to be affected by the gravity in the same way that cannonballs, rockets, and planets are. And the first people thought that the particles of light traveled infinitely fast, so gravity would not have been able to slow down them. But the discovery by the Romer that light travels at a finite speed means that gravity might have an important factor.
On this assumption, a Cambridge town, John Michael, wrote a paper in 1783 in the Philosophical Transactions of the Royal Society of London, in which he pointed out that a star that was sufficiently massive and compact would have such a strong gravitational field that light could not escape.
Any light emitted from the surface of the star would be dragged back by the star's gravitational attraction before it could get very far. Michael suggested that there might be a large number of stars like this, although we would not be able to see them because the light from them would not reach us. We would still feel their gravitational attraction. Such objects are what we now call black holes, because that is what they are, black voids in space. A similar suggestion was made a few years later by the French scientist the Marquis de Laplace, apparently independently of Michael. Interestingly enough, Laplace included it only on the first and second edition of his book, The System of the World, and left it out of later editions. Perhaps he decided that it was a crazy idea.
In fact, it is not really consistent to treat light like cannonballs in Newton's theory of gravitation because the speed of light is fixed.
A cannonball fired upward from the earth will be slowed down by the gravity and will eventually stop and fall back. A photon, however, must continue upward at a constant speed. How then can Newtonian gravity affect light? A consistent theory of how gravity affects light did not come along until Einstein proposed general relativity in 1915. And even then, it was a long time before the implications of the theory for massive stars were understood.
To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction.
As it contracts, the atoms of gas collide with each other more and more frequently and at greater and greater speed. The gas heats up. Eventually, the gas will be so hot that when the hydrogen atoms collide, they no longer bounce off each other, but instead coalesce to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the star shine. This additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction and the gas stops contracting. It is a bit like a balloon. There is a balance between the pressure of air inside, which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. Stars will remain stable like this is for a long time with heat from the nuclear reaction balancing the gravitational attraction. Eventually, however, the star will run out of its hydrogen and other nuclear fusions. Paradoxically, the more fuel a star starts off with, the sooner it runs off. This is because the more massive the star is, the hotter it needs to be to balance its gravitational attraction. And the hotter is, the faster it will be use up its fuel. Our sun has probably got enough fuel for another 5,000 million years or so, but more massive stars can use up their fuel in as little as 100 million years, much less than the age of the universe. When a star runs out of fuel, it starts to cool off and so to contract. What might happen to it then was first understood only at the end of the 1920s.
In 1928, Indian graduate Subraman Chandrasekhar set sail for England to study at Cambridge with the British astronomer Sir Arthur Eddington, an expert on general relativity according to some accounts. A journalist told Eddington in the early 1920s that he had heard that there were only three people in the world who understand general relativity.
Addington paused, then replied, I am trying to think who the third person is. During his voyage from India, Chandrasekhar worked out how big a star could be and still support itself against its own gravity after it had used up all its fuel. This idea was this: when the star becomes small, the matter particles get very near each other, and so, according to the Pauli exclusion principle, they must have very different velocities. This makes them move away from each other and so tends to make the star expand. A star can therefore maintain itself at a constant radius by a balance between attraction of gravity and the repulsion that arises from the exclusion principle. Just as earlier in its life, gravity was balanced by the heat, Chandrasekhar realized, however, there is a limit to the repulsion that the exclusion principle can provide. The theory of relativity limits the maximum difference in the velocity of the matter particles in the star to the speed of light. This means that when the star got sufficiently dense, the repulsion caused by the exclusion principle would be less than the attraction of gravity. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the Sun would not be able to support itself against its own gravity. This mass is known as the Chandrasekhar limit. A similar discovery was made about the same time by the Russian scientist.
This had serious implications for the ultimate fate of massive stars. If a star's mass is less than the Chandrasekhar limit, it can eventually stop contracting and settle down to a possible final state as a white dwarf. Lanto pointed out that there was another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the Sun, but much smaller even than a white dwarf. Stars with masses above the Chandrasekhar limit, on the other hand, have a big problem when they come to the end of their fuel.
In our discussion, we have proved that a black hole is formed only when the mass of a dying star is greater than the mass of Chandrasekhar limit.